Welcome everybody to this second session of this training in machine learning methods for the analysis of migration trajectories. I would remind you that this training is sponsored by the Scientific Panel on Lifetime Migration of the International Union for the Scientific Study of Population. You can check out the website of the IUSSP for more information on this or other future events of this scientific panel. I'm very happy to introduce today, very briefly, the lecturer of this session on feature selection approaches. This is Danilo Bolano. Danilo Bolano is a research fellow and a lecturer at Bocconi University Carlo Dondena Centre. Danilo is an expert on life course research and the development and application of associated quantitative methods, such as the one he's introducing today. And he is currently the principal investigator of a research project on internal migration and resilience of the European regions. So Danilo, the floor is yours. Thank you so much for being here today.
Thanks, Sergi. Good morning, everyone in the room. Good morning, good afternoon for people from home. It's a pleasure to be here today to discuss a little bit this topic. Before entering in the real topic of today's presentation, I just want to give you a little bit of the take-home message of this presentation, in particular for more younger students or people that are starting a PhD or early career researcher. I mean, and how we, my colleague and I, end up doing this kind of work is the idea that we usually in social science tend to be quite conservative in the empirical statistical approach that we use to analyze data. We tend to focus on one and get straight on. But there are many statistical approaches that can be used. So the idea behind this work, and I hope you will see by the end of this presentation, was to try to bridge a little bit between two kind of approaches. One was a sequence analysis, and the other one were feature selection and machine learning. So how the two a little bit different things can talk to each other, and this can be expanded in many different ways. This has been mainly my activities over the last 10 years, trying to bridge stuff from different fields and how to see how things can work together. Again, before entering after this take-home message, I have a disclaimer. Sorry to disappoint you, but this will not be a class on machine learning because 2 hours is not enough to discuss about machine learning. This will not be a training on how to use fancy Python things. We will use some R code to do things. Again, this is just a different way, starting from what Professor Vidal discussed in the previous 2 hours of this class, how to likely looking at sequence analysis in a slightly different way using machine learning techniques. And again, a little bit of a step back, how we end up doing this. As Sergi mentioned briefly, my work has been in the life course paradigm. This is a very general framework to analyze social science research questions. And the idea behind this, the life course paradigm, this is not a theoretical sociological theory, it's more a paradigm, is the idea that if we are looking at the trajectory of the individual, so if we are looking at how people have lived their life, we have to consider that this is the result of the interaction of many things. This is the interaction in location and time and place. So the idea that, I mean, for instance, people in the room, the fact that you are doing a DSD now in Barcelona has an effect, will have an effect in a way or the other to your life course. But then there's the question of human agency. Every people can make their own decision based on expectation, constraints and stuff. Then there is the question of linked lives, and so the social network, the idea that you are strictly linked to people that are belonging to your network. Then there is H-period cohort effect. So everything, according to this paradigm that has been developing first in the 70s and then in the 90s, is everything is interacting, everything is going together to determine how people are living their life. So the life course of the individual. So if we believe that this is the paradigm to consider, then when we're thinking about the life course of the individual, when we're thinking about the life trajectory of the individual, we should remember that this is the result of the interaction of many things. many things that should, in a way, be taken into consideration together. And we can think about the life course paradigm as a way of studying the different forms and dynamics that we observe in life trajectories. The key elements of the life course are the concept of events, the transitions, the idea of phase, the idea of trajectories. And we can use the life course paradigm as an umbrella term, as an umbrella paradigm to do many things in social science. We can think about these to reply research questions as identify typical or not typical to non-standard trajectory patterns. So how either are common patterns that we observe or not. We can cluster individuals together. So how we put together homogeneous groups of individuals and see what's the characteristics of this individual. We can study individual trends or growth pattern, how people respond to give critical events, so the idea of within individual differences or between individual variations. Or we can use as to study duration models or the time until a given event. And to do that, the approaches are various. The traditional one are event history analysis. People from IUSSP have heard about this, so I will not spend time on this. Then we have random and fixed effect model, where the idea is more to looking at the effects of variation that happen within the trajectory. So this is commonly used to see the effect of a critical event on the life trajectory of the individual. Then we have dynamic model, where the idea is more a multi-state kind of approach. So moving from one condition to another, what's the probability of moving from one situation to another? Like, let's think about, for instance, health condition, or moving from a good to a worsening health condition. So that was also transitional model, and then sequence analysis that you have seen on Tuesday, where the idea is to looking at the trajectory in a more holistic approach. So looking everything all together, and then the goal is not just looking at something that happened in a given moment, like the transitional model or macro model, but to look at the entire pathways. So as Professor Vidal discussed on Tuesday, sequence analysis that can be seen as an analytical approach to study many things is a descriptive tool, as you were saying, but the idea is looking at the trajectory, how people are different to each other. And the objective of sequence analysis, at least in a social science perspective, can be exploration. So to see how the sequential data looks like. How similar are the sequence, or how similar individuals are to another, and group together individuals belonging to similar clusters. So looking at some patterns, some trajectory patterns that we're observing. This is what's called an holistic approach, because the idea again is to looking at the entire trajectory as a whole to determine to study the life trajectory in the life course of the individual. And the 3 steps to usually do the sequence analysis approach, again, you have seen already this, so this is one going quite quick, is to, well, starting from the data, you need to create your sequence, so an ordered sequence of sequential of states. So you have categorical state, and then you put in an order. The granularity depends on your data. It can be daily, hourly, minutes, year, whatever, but the granularity must be the same along the study. And then you see how the order of the events looks like, and then you try to graphically represent them, and then you have this very nice plot with all the colors and stuff. The second step is to compare sequence. So you have an order of states for one individual, you have an order of states to another individual, and then you compare pairwise, one by one, all the people that or the units of interest within your data frame. And then you use some dissimilarity metrics to assign similarities or not across the individual. Are these sequences similar to sequence 2, sequence 3, sequence 4, 5? And based on this dissimilarity measure, and there are many similarity measures around, based on this similarity measure, you can create typology, putting together individuals that have similar characteristics, so a small dissimilarity. So the intuition is, okay, the life course of the individual, we try to identify individuals that have similar life courses and putting together in a cluster. This is more or less the bottom line of sequence analysis, and there's also bottom line of what Professor Vidal discussed. Probably what Sergio wasn't able to do in 2 hours is, okay, this is theoretically, but in applied research, how this looks like. There are now many studies using sequence analysis. It's becoming extremely common in sociology, but also in health research, social demography. When you have longitudinal data, it can be either retrospective or prospective data. It can be survey data. It can be data from administrative sources. Any type of longitudinal data. Here I'm presenting one of many studies that use sequence analysis. This is taken on a paper of Ferrari and Payet from Advances in Life course of a few years back, where one of the goal is to compare second generation migrants to native French. So what they did is to took the life course trajectories of a very large set of individuals, the trajectory from age 15 to 30. So the focus therefore was on transition to adulthood, or in the first phase of the adulthood of this individual. So they have a group of French natives and group of second generation migrants, so children of migrants. This is a very applied paper where they trying to test 3 research hypotheses. The first hypothesis were more in the of cultural background, in the sense that second generation are more likely to follow standardized pathways to adulthood, so childbearing within marriage and kind of things. Another hypothesis they want to test was more sociological, socioeconomic hypothesis, in the sense of looking at difference also within the group of second generation migrants between people from North Africa and other parts of the world. And according to the hypothesis, they might have leave the parental home later, more likely to marry unemployed, and so. And then there is a gender hypothesis that they want to test. Also, again, looking at this trajectory, are there a difference between men and women, also within native and within groups of second generation migrants. Okay, so this is a very applied paper. What they did is they had longitudinal data on residential, work, and family life. So they know if the person was living or not with a parent. They knew if they were studying, or it was employed or unemployed, if they were single or was cohabitating, single or living with other people, cohabitate or in cohabitation, were married, if they have kids or not. What they did is have this sequence of 3 life domains, so residential, work, and family life. They create a multi-channel approach that I don't think Professor Vidal had the time to discuss. Is just an extension of the classical sequence analysis, where the idea is to consider multiple trajectories for each individual. So instead of having one line of observation for each individual, we'll have multiple lines of observation. One trajectory for family, one trajectory for work, one trajectory for residential. And they identify some clusters, so group of individuals that have similar characteristics, they have similar pathway in these 3 life domains, and they analyze how this transition to adulthood was shaped by cultural and socioeconomic factors. So the outcome, classical outcomes in a sequence analysis paper are this clustering, so they graphically represent, and then you look a little bit of the colors, and you're looking at the states and try to interpret. This is a classic like cluster approach, in which you identify some clusters and then you try to give a name. So you try to label in the clusters, right? And this is common to Latin class analysis, cluster analysis, or this kind of cluster analysis. In this case, they have already identified 5 of them. This is therefore 3. So it's a group of people that were living single for more time, and then married, and then were stay a lot of time in studying. People that were moving fast to marriage and fast to parenthood, so they have a transition to the first child quite quick. People will stay single and then start cohabitating. Those who are leaving the nest quite late, so people stay long at home and then move on. People, and this is usually women, that start having a partner very early in life, but they stay also unemployed. So they not find a job straight away, at least in this first 15 years of the reality. And what they do is to use the cluster. So, and in this kind of approach is a kind of deterministic clustering. So you belong to one specific cluster. So each individual will belong to one of these 5 clusters. So you end up like a multinomial situation where you have a variable that goes from 1 to 5, belonging to cluster 1, cluster 2, cluster 3, cluster 4, cluster 5. And the traditional approach is you have this variable that you use like your dependent variable in regression settings, and then you see which are the characteristics that make you more likely or less likely to belong to one cluster or another in a very traditional regression setting, okay, where your y variable is the cluster, in which cluster the individual belongs, and then you have a long set of controls and a variable of interest. What they find, this is not really relevant for but just to give you an idea, that the second generation migrants frequently follow paths with long period autonomy and more economically constrained pathways. They stay significantly longer in parental home, in particular children of migrants from North Africa, and in particular women. The entry into adulthood or the transition to adulthood autonomy is much slower with respect to other groups. But this is just to give you an idea how usually sequence analysis research is done. You have your trajectories, you create clusters, and then you use your cluster, and you try to identify which characteristics make you more or less likely to belong to a given cluster. So in this case, the life trajectory or the cluster in this case is the outcome variable, is the y variable that then you apply a regression set. There are other approaches where it's the other way around, in which the life course of the individual is used as to predict something else. So is the variable of interest with respect to another. And this is is quite common in a topic in social science or sequence analysis more generally. We can think about testing cumulative advantage to disadvantage theories, or the fact that you have lived your life in a given way can be associated with some situation, or for instance, wealth inequality later on in life. We can also think about identifying which characteristics or which life events. It can be a given transition, it can be something that happened in your life as an effect later on. I put here just a few examples. I didn't put the references back because there are many references, but this is taken from real paper looking at working trajectory and the later life economic inequality. So the idea that you show that according to your working condition, the wealth or the economic condition will change, but also an accumulation that happened over the life course. And in particular, this is also can go a little bit back to like more economic theory in terms of unemployment, unemployment spells in particular phase of your working life as a more or less stronger or weaker effect later on in life in terms of ability to earn higher wages and stuff. Migration pattern is also being seen associated with wealth. The idea of family life and health, also in this case, you took the life course of an individual, the family life course of an individual, so you see when the people start to have kids, etc., and then see how this is associated with well-being, physical, mental health later on in life. Again, with the idea of accumulation of disadvantage over the life course. Housing tenure, living arrangement, and criminal activities. So as you can see, there are many different approaches that then have been used in the literature. And here the approach is I look at life course of an individual, I have an outcome measured later on in life and see how these are associated. And if you're looking at the literature, what you see to analyze this kind of association, at least in social science, so we're not going more in like causal analysis, it's more social discovery phases of studies or associational studies, is either you pre-identify a small set of indicators, And then you use this in a regression settings. Let's say that you're looking at working trajectory and economic inequality later on in life. You have your measure of inequality, can be any kind of measure. And then you say, okay, I'm interested in seeing if this person has ever been unemployed over time, if this person entered in the labor market before or after a given year, and so on. And usually this is very theory driven in the sense that, okay, I have some theoretical framework that I want to test. And I put in my regression setting these indicators that I'm interested, plus a set of controls, and then I see if the association holds or not. If I got my stars in my table, I'm happy and say, oh, my thesis is my hypotheses are true, and then move on. The problem of this approach is that you must choose a priori these indicators. It's something that you have to create ex ante from your data, and then you are testing if it is associated or not with your outcome. And the other critical points here, in particular, again, if you believe on the life course paradigm where everything is connecting with everything, so a life course of an individual or life trajectory of an individual are more complex than a single measure or single indicator, then previous trajectory can be more complex. Perhaps you are creating an indicator that makes sense from a theoretical perspective, and perhaps you find an association with your outcome, but perhaps that indicators are behind that indicators there are many other things that you really cannot see because you are adding one single variable to your model. And usually this kind of work is focused on duration, for instance, how many years of unemployment you experience, and then how this is associated with wealth at 50, or critical events, motherhood death, for instance, the fact that you have a kid at some point in time, how does it affect your wealth later on in life. The other set of approach that has been done are belonging to the sequence analysis, and we are going back to square one, where the idea is, okay, the life course is more complex, and I want to have an holistic view of the trajectory. So instead of using one specific indicators, what I see, I take the entire life trajectory of the individual, I create this cluster usually, and then I use this cluster to predict the wealth inequality or an outcome later on. This makes sense because you can see many things. You can see very specific pathways or very specific groups of individuals. But the main negative point is that the clustering is a black box in a way, so you don't really know how this is being put together. I mean, you know at the end how the clusters looks like, but the clustering per se is a black box. Labeling can be tricky. I mean, once you have the cluster, you can plot, you can do many things, but then it's up to you to decide the name of the cluster, to interpret the cluster in a given way. I can interpret your cluster in a completely different way. It is very hard to justify, oh, this means this, in particular when the clusters are a little bit messy, is not very standard. And the other things is that by definition, the clustering approach works in reducing complexity. So the idea of the cluster is putting together things that are similar to each other, but without really taking into consideration that so there is an oversimplification risk. Perhaps there are small differences that are ignored simply because we are putting the clusters together. So what we suggest in a paper with Matthias together, this is what I'm going to present today. Matthias is a professor at the University of Geneva, is to try to combine a little bit these two ideas. To combine the idea of the sequence analysis and with the idea of the indicators. So the starting point of this is, let's using machine learning technique or feature selection techniques better to identify which are the characteristics of the life trajectory that matter to explain a given outcome. So the starting point will be a way to create the life course of an individual, the life trajectory. So we still have this kind of holistic approach. But once we create the sequence, then you create out of this sequence a set of indicators. So we're going back a little bit to the first point, so the creation of a set of indicators, and then using feature selection algorithm to identify which characteristics matter to explain your outcome. So we are trying to bridge again a little bit the idea of sequence analysis and the idea of looking at things, an overview look at things with more machine learning or feature selection algorithm. So the proposed approach that you will find now still in a working paper is we start creating the sequence. We will do this together on in a second. We create the sequence like in the sequence analysis approach, and then we automatically identify or automatically extract the features, what we call sequence features. So there are some characteristics of the sequence that matter. We will see what this means. And once we identify this long set of features, this is a long set of variables, then we apply feature selection algorithm, because we have a long set of characteristics, we have an outcome of interest, so we can apply some supervised learning approach to identify which of these characteristics really matter to explain our outcome measured economic life. In the paper and also in this presentation, I will briefly discuss two automatic feature selection algorithms, one based on random forest and the other based on Lasso. There are many different feature selection algorithms around. The goal of the paper is not to say, oh, these are the most relevant, but we believe that these two are relevant for a social science perspective, and I will discuss in a second why. We will have two empirical examples. In the slides, you will find empirical example, the results very similar to the one that is on the working paper that I mentioned before. The other example that we do in R will be following what Professor Vidal did on Tuesday. So using the same kind of sequence, how we can test this feature selection algorithm on this. And in particular, in the first in the slides, you will see a study on looking at work and family trajectories, how these are related to inequality in income later on in life. This is among women. And instead, in the R code, as we have seen on Tuesday, we will look at residential trajectories, so moving between low, medium, and high SCS neighborhood, or being outside the big city, and how this is linked with health. And we will use a standardized health indicator that I will discuss later. So others, let's stop here for a second. Do you have any questions, or this is clear? Yes, please.
Do you use the algorithm to decide?
Yes, we use the micro, because the online audience thinks.
Do you use the algorithm to choose the indicator, or do you already set the indicator and the algorithm chooses which ones are more relevant?
No, the idea, I mean, you can do two things. The idea here is to extract as many information as possible from the data. And then, of course, it depends a lot from the theoretical framework, or a little bit from the hypothesis that you come from, because they might have some features that are not relevant for your cases, other than they might. So the approach that we suggest is to extract as many information as possible, but in a way that should be related a little bit to what you are interested in, because there are some characteristics that perhaps you are not really interested, or this is not the focus on the work. So yes, is data mining in a way, in the sense that you can let the approach identify any characteristics of interest, and then you select using the feature selection algorithm, or you do a kind of pre-selection. This is not a really pre-selection, you just try to identify which general features that you might be interested in looking at. But I think in a second will be more clear. Do you have any other question from the audience? No. So let's move to. So just briefly to explain what is the empirical study that you will see in the slide. So we are using work and family trajectory between age 20 and 40. And how these are associated with the personal income of women in midlife, so 50 plus. These are data that are retrospective data from the Swiss Social Panel. And why work and family trajectories might be associated with income? Well, theoretically, there are many potential mechanisms behind. Of course, there is how much time you spend outside the labor market. This influence your ability to accumulate income and wealth later on. You can have then this might be very much related to human capital depreciation or scaling effects, but there are multiple aspects of unemployment might be associated also probability to have less or more wealth later on in life. Then there is the motherhood marriage penalty or the motherhood gap. So the marriage penalty and the motherhood penalty, so the fact of having kids usually has a negative effect, but also if you have kids, perhaps you need to work more hours to make the needs, etc. So there are many potential mechanisms behind it we could test. This was very interesting because at the same time we were doing this, a paper in Demography came out saying exactly this, that family trajectories are very much associated with women's later life income. And this is a paper from Muller, Eichel, and Lifbruer in Demography in 2020. And it was very interesting because they were using the same mechanism. And in the paper, what they say is that, okay, and they use sequence analysis with the cluster, the approach, the usual approach that we say is towards the conclusion of their approach, their paper, they say, this is what we observe, but we cannot say which characteristics really matter that we observe in the cluster to explain the variability. This was exactly where we're going towards in our approach. Clusters are a very useful approach because it's very easy to do, and then you can explain a lot of things, but then within the cluster, it's very hard to identify the characteristics of interest, at least in the traditional way of doing clustering approach. Then there is also another field of study within sequence analysis where they try to develop new way of looking at the clustering approach, where it's not more deterministic, but it's probabilistic, and is start to fuzzy clustering, so more complex kind of relationship in this kind of approach. But still, overall majority of studies used in sequence analysis use very traditional deterministic clustering approach. The other empirical study, well, you have already seen this on Tuesday. We have migration trajectory or better residential histories on 800 residents in Chile. You have these 5 states living outside in Santiago or living in the low, medium, high income neighborhood. And we want to see how this is associated with health. Why it's relevant? Because, well, living in low SES areas can have a long-term effect on health. We can have also positive effect from upward mobility, in a way, upward mobility observed via the mobility of residential mobility. There are people that have discussed about the effect of multiple residential change in early childhood. This is a paper published in Health and Place where there is a meta-analysis that looks exactly like this, and then they show that having many changes when in childhood residential changes is have a long-term negative effect on health. So what we are doing is to try to see how this works with our approach. So as mentioned before, the approach that we propose works in 2 steps. The first step is to extract the features. Again, this is go back a bit to the previous point. We can decide the way to extract the features. We can extract any characteristics of interest from the trajectory. Or we can say, oh, might be interested in some macro groups of variables, macro groups of features that are interesting. Again, what we use is a life course perspective in this kind of work. So the macro groups of characteristics that perhaps matter to explain inequality later on in life are related to the critical periods, like theoretical framework. So the timing, when something happened, when the person had the kids, when the person moved from one area to another, when the person had lost the job, etc. So the idea of timing. And then you can do this over the entire trajectory. For instance, here, let's say, okay, this person have moved to the brown state between the age of 23 and 27. So in that period of time, a transition happened and this person ended up on this condition. This is a fictitious sequence, just illustration. And the other macro group of features that might be interested are related to exposure. So the overall time spent in a given condition, how long the person has been married, how long the person has been living in a low SES area, how long the person has been unemployed. So the idea of exposure, if you want to think more in a health perspective, or the duration, if you want to think more in a sociological perspective. So how long the person has been living in a given condition. Then the notion of occurrence. So which state the person has observed? Has this person ever been unemployed or not? Haven't been in a low SES area or not? So which state the person have been observed over time? And very much related to this, there is also the concept of order of states. And again, this is one of the key features of sequence analysis, the idea of looking at things ordered. So we can use the concept of sequencing or subsequencing to identify which are the situation in which the person was. Okay, we observe the person that was in a low SS area, but does the person before was living in a same area, a different area? So we're looking at an upward mobility trend, we are looking at a down mobility trend, or if thinking about the working trajectory, are this person moving from full-time, part-time, and then outside the labor force, or this person was education and then went straight outside the labor force, this kind of patterns. So any kind of patterns can be extracted from the data. Just to give you an example of what does it mean, this is our 3 fictitious individuals observed between age 20 to 30. Let's say we have this 5 conditions. The person was in education, if they were in observing the green one. We either state if it is missing, in this case it's not relevant, part-time in the blue, full-time in these violet things, and not working in yellow. So we have the individual on top that was full-time from age 20 up to age of 32. Then this person went to part-time afterwards. The second individual was full-time, then moved to not working, and then back working in at age 37 and 38. So it's from yellow to blue. The last one was in education for the first 3 years, and then in full-time. What the approach does, very simple, is for all individuals, we extract all the information that we want. For instance, occurrence and sequencing, we say, does the individual was in full-time? Individual in the top was ever in full-time? Yes, because we observe a purple state somewhere. Individual in the middle as well, individual on the bottom as well. Does we observe a subsequence full-time, part-time? So has the person ever been in full-time and then later on in part-time? So does we observe the purple and then the blue things? Yes, we observe in the first one. Yes, we observe in the second one because it was purple here and blue here. So 1, 1, 0 for the person at the bottom. And then we can see this for any possible combination of the states. So here we have 5 states. So we can say sequence of education, part-time, full-time, education, part-time, full-time, not working, education, part-time, not working, full-time. So any possible combination. And as you can imagine, the number of subsequence easily explode. If we just have ABC as states, so we can see if the person was ever been in condition A, yes or no, in condition B, yes or no, in condition C, yes or no, ever been in condition A and B, in condition A and C, in condition B and A, in condition B and C, in condition C and A, C and B, etc. So increasing the number of states, and luckily now with longitudinal data, we have very detailed information. So what's called the alphabet of the sequence is easily large. This number can explode. Then we can identify some timing feature. For instance, does the person have stopped education between age 20 and 24? And yes, for the individual. then we can extract information about the duration, how long the person was in full-time, part-time, etc. So we can do this for any kind of, we do this for all individuals, and this can be this multiplied. Then we can include, as we will see in the R code, we can include the transitions, how many times a person moved from one condition to another, and so. In our example that we have in the paper, we have full-time, part-time, not working education states for professional trajectory. We have for family lives, we see if a person is single, if living with a parent, with a partner, living with a partner and having kids, if she's living alone with children, or she's living in other living condition, living arranged condition. So even here we condense the type of features that we are interested in. We identify, we can extract 34 features related to timing, so when an event happened. We have 10 variable about duration, one for each state. Then the sequencing, we restrict to looking at the subsequence or the pattern we observe that are at least in X% of the sample, and we end up with almost 30. But if you put in everything together, we end up with 180 variables, 180 features. And again, we have restricted this to the things that we think might be relevant. If we let the model identify all the features, this number will be enormous. Let's see how did this look like in R. So you have received the R code and the script. So the data are exactly the same that you saw on Tuesday. Is just one additional variable. This is outcome variable that we are interested in. So there are a series of packages that we are going to use today. One is Traminer and Wooded Cluster, which you should have seen already before. Then also we will use Boruta to do random forest, and we will start to do the Lasso. And eventually we will do some graphical representation if we have time with ggplots. So as usual, when we start things, we create a working directory. More data person will say, "Oh, never use set working directory, is a bad things to do in the code, blah blah blah." But okay, we do set working directory, and then we load the data. So the data, how it looks like. So we use the function name to identify the name of the column, and the view to see how it looks like. So we have all the information for each individual. And then at the end, we have a variable called outcome, that is the one we're going to use. So the first step of the approach is to create the sequence, because the feature will be extracted from sequences. And then we will use Traminer and the function secdef to define the sequence. I think I certainly described this already. So what we do, we have an alphabet that goes 1 to 4, and then 1 is in low SES, 2 is in mid SES, 3 is going to be high SES, 4 will be outside Santiago. That's here. This is the label. We can give the color palette. So this is color that we want to use the first, the second, the third, but then you can play around with the colors and see how it gets. So we define the sequence, then I think we can graphically try to graphically represent them. I didn't load my libraries. So, Anyway, it doesn't matter. So the feature extraction, so the first step is a step 0, actually was to just identify the features, so to create a sequence. The second one is to extract the characteristics of interest. Here we extract slightly different characteristics than the one we have seen before. You can use the function sec_prop class from the weighted cluster library. For instance, we will extract duration variable. So we'll have the duration below. So the first person was 6 years in a low SES neighborhood. The second person was 0 year, etc., etc. So for each individual, we have the duration which the person spent in each of the 5 conditions. So low SES, mid SES, high SES outside. Then we can give them a more nicer name with a +0. So we have duration low, duration mid, duration high, and duration high. Then we say, okay, we have the duration because we're interested in how long the person was exposed to a given neighborhood. Maybe we might be interested also in see the pattern. So are the person moving from high SES to low SES or from low SES to high SES? Always within the same function sec_prop class, we can have the command properties equal to pattern. That extract all the subsequence, so all the possible patterns that we observe in the data. And then here we are adding an additional command. This is fill-in support. So what is saying here is that let's keep only the patterns that are observed at least in 2% of our sample. We can also delete this and then it will extract any possible features, any possible combination that we observe in the data. But let's say for interpretation that we are interested in looking at the pattern that are observed only in at least in 2% of the cases. What this number means is that, for instance, so this is the pattern from outside to the city going to a mid SES. This person has been observed doing this 2 times. So within the same trajectory, this individual 2 times has moved from outside to the middle. So it means that this person is moving a lot from in and out, in and out. Then you can choose. Here we decide to keep the number of times we observe the pattern. Or we can also say, oh, we are not interested in the number of times the person has experienced the pattern, but we're only interested in is the person experienced the pattern or not. So using the dummy variable, we can do that. We just record this and say, are the individual observed at least once doing this pattern, yes or no? This is up, again, this is up to the theoretical framework and the things that we are being interested in. And here, let's say, I show here in the room. As you can see in the bottom of the console, this is all the patterns that are observed at least 2 times in the, at least 2% of the time. So people that go to outside to mid and then something happened and then they go back to mid SES. There are people that are in high and then move to mid. There are people that from a low goes up to mid SES. So we can see all the possible patterns that you observe in the data. You can do also this in one single step instead of doing this. Within this sec_prop cluster, there are also other features that you can extract. For instance, the duration of the spell. Let's say that you are interested for how many spells of living in SES, in low SES neighborhood the person was, and I'm interested to looking at duration of each of these spells. So we have a first spell in SES of X year, a second spell in SES of this length. This can be, for instance, very useful if you're looking at more working trajectory, and we think about spell of unemployment. So how long was the first spell of unemployment? How long was the second spell of unemployment? How long was the third spell of unemployment? So then we can also identify some complexity measures. I don't know if Professor Vidal discussed this, but one way of looking at the trajectories is also to create some indicators. Is a single variable, is a continuous variable that explain a little bit of the variability. If you have a background in mathematics, you remember concept like turbulence or these kind of things is more or less the same things. How much variability we observe within the trajectory, how many changes happen in the trajectory, and we create a unique indicator. This is also something that you can extract within this SecProp cluster variable. Instead of using complexity or other kind of complexity measure, we can also simply say, okay, I'm interested in the number of transitions that I observe. Because some theoretical framework that I've discussed before has been found that having multiple changes really matter to explain health condition later on in life. So there is a function within the terminal that's called sec_trans n that gives the number of transitions that I observe in the sequence. So you can create this additional feature. This is the number of transitions. And you can see there's a lot of heterogeneity in our sample. The first individual went through 7 transitions. The second one only 1, so it was more or less stable pathway. The third 4 times, and so some individual never changed. So a number of transition was 0. I mean, that person was in the same condition for his entire life, or in the same SCS neighborhood for his entire life. The other things that the literature shows us is relevant is the timing of the transition, when the person has moved and where. So we can also extract this. I don't have the time to go to the code, but I mean, this is still in development, and the long-term plan of Matthias and I is to put all this function within a unique function where you can extract everything at the same time in an easier way. I don't have the time to go in the detail of all this code, but this code is just say I pre-select some kind of transition that I'm interested. For instance, in this case, I'm interested in the transition from low to high SCS, or from mid to high SCS. So in the idea of upward mobility, when the upward mobility happen in the life course, or the other way around, when they're moving down. So when this transition from high to low happen, or from mid to low happen, to see perhaps people that move into a low SCS neighborhood early in life have a stronger negative effect than people who move later on, or vice versa, I don't know. Or when any type of movement happens, so from low to mid, low to high, etc. Running this, you will, and then for simplicity, we create age group of quite large here, quite large groups. Let's say between the first 25 years of observation, from 25 to 50, to 50 to 65. Had this person ever moved, the first individual ever move up between the age of 1 and 25? Yes, 1. The second person, no. Does the first person also have a moving down in the same time frame? Yes. So this person was clearly moving up and down a lot. And you do this for any kind of transition. I mean, again, here we pre-select some groups of transitions we're looking together, but again, if you want to be more data mining, you can say extract any transition that you observe to any point in time. So you will end up with a variable say, are the person at age 2 ever transition from A to B? Have the person ever been transitioning from A to C at age 1, etc., etc. So even you explode again the number of students. So just here, in a way, we consider only the transition, the features that we might think are relevant. Only in this case, we end up with the 58 variables. So in the previous example, it was, I mean, in this example in the paper is 100 and 20. Here is around 6. But still, this feature, we cannot just put this in a regression settings because these features are highly correlated to each other, right? So if we run a regression model with all these features all together, the variable, the model will eventually converge, but we have features that are variables that are highly correlated, and so the results will be impossible to interpret. So the idea of feature selection at this point is say, okay, instead of using traditional regression approach, how I can identify which of these features really matter to explain my situation later on. So before moving to the feature selection part, that's a little bit the idea of the extraction of features work for people from distance.
Online, no questions, but
In the room, there are no questions either. So the first step is to identify the variable. With the second step, and then we can take it a bit slowly here, is to select the relevant features. So again, we are in the settings of supervised learning, right? We have an outcome of interest that we are looking at, and we have a set of variables that we are interested in. So it's not clustering anymore, it's not unsupervised learning because we have one specific outcome of interest that we are looking at. That's women income in midlife, in the example in the slides or in the paper, is that outcome health indicator in the output. So the goal here is to identify which features are statistically linked with the outcome of it. The problem here are multicollinearity. I just said this second before. We cannot put all the variables together because these variables are highly correlated. By definition, are highly correlated. Then there is a problem of multiple testing. Again, it's true we are not in like a big data framework with thousands of variables and thousands of observations, but still multiple testing is an issue. If you're using a 5% classical test, you will end up selecting wrong features. So multiple testing is an issue to account for. Again, that's the reason why we cannot just put everything together in regression settings. And also we were interested in indirect relationship among the features. Again, these features are highly correlated. True. But also if we are, again, in the life course perspective, we know that one characteristic might be linked to something else that I have in the data. So I want to also to looking at indirect relationship that happens between features. So how these features are interacting to each other. Perhaps moving from a low SCS to a high SCS is relevant, but is also relevant, for instance, if you have lived outside Santiago for some time or not. So we need to, we want to see also this indirect relationship and interaction effects in a way. So the approach again that we use in the paper are based on random forest and Boruta, and the feature selection algorithm based on Lasso. It's called stability selection. We focus on these two approaches. Again, not because these are the only approaches available, not because these are the best approach that you must use, but it's two approaches that takes very different point of view, and both we believe are running together and looking at the results of both approaches at the same time give you a good overview of what happened. Because Boruta is also known to be all relevant feature selection algorithm in the sense that it will give you a general overview of things, how variables are linked to each other in a more general way. And then I will be back to the business. Lasso, as you probably have already used, is a known best predictive feature selection algorithm in the sense that Lasso tries to identify which variable of interest has the stronger predictive power on the outcome. So with Lasso, or stability selection is an approach based on Lasso, you will end up with very few number of features that really matter. But then again, since we are in a social science perspective, and we are also interested in interpretation of our results, we're also interested to have a more broad view of what happened, broader view of what you're looking in the data, and is what Boruta can give us. Let's do a very, very small parenthesis on feature selection algorithm. Again, this is not the goal of the day, but just to give you also a little bit of terminology that perhaps can help later on to identify which characteristics are which kind of algorithm you are interested in identifying. So, generally speaking, there are three main groups of feature selection algorithms. There are what they call filter methods, where there's mainly no algorithm attached to. And I mean, you know this very well. This is chi-square test, ANOVA, are also considered as a feature selection algorithm in the sense that you are testing the association between variables, and you can decide to keep or discard the variables that are not relevant for your cases. So even if we didn't know, but even just doing the ANOVA and then selecting the variable, you are doing kind of feature selection things. Then there is the wrapper methods that are based on specific algorithm. And here the intuition is to evaluate all potential combination of variables. And then this is evaluate against a criteria. It can be accuracy, precisions, the p-value, and so on. For instance, the stepwise selection that perhaps many of us have tried to use is actually a feature selection algorithm. Is actually a wrapper methods for variable selection, because what they do is iteratively adding variable and excluding variable to the model until you find a subset of variable that matter. So you are already doing feature selection, okay? But then there are more complicated and more interesting approach and the random forest and the others. Then there are the third groups that are called embedded methods that are usually, but not all, based on some penalization coefficient. And Lasso belongs to this group of embedded methods, and ElasticNet as well, etc. So the idea is to have a penalization coefficients, testing the variables and giving a higher penalization to the variable that doesn't matter anymore to you. Well, we'll go back on this. So broadly speaking, excluding the filter methods because they are less relevant in our case, and there are many methods that are a mix of things. Huh? Okay. This is a very broad division of approach. We can think about the wrapper methods as a way to see also the interaction between things, how all the variable going together. When instead the embedded methods is approach that allow you to have a more predictive power, to identify which variable have higher predictive power in their model. So this guy, sorry. I was trying to get rid of the. Sorry. I was trying to get rid of this. I can't. Okay. All right. This guy is Boruta. Boruta is the Slavic god of the forest. And the approach that we're using, we didn't develop, is a very well-known algorithm, is an evolution of random forests. So the people who developed this and developed their package and say, oh, let's call it Boruta because Boruta is the god of the forests. What Boruta does is an extension of random forest. So it belongs to the group of the wrapper methods that we see before. So before going to Boruta, just a quick recap about random forest, because I mean many of you have heard about, but just to have an idea, is a series of decision trees, each of them built over a random extraction of variables and a random extraction of data, so a subset of the data. And each tree is a sequence of yes or no, selected or no, based on a single or a combination of features. So the idea is to identify the first variable that matter among all the variables that you have for each single tree. Then you do this, then you move So let's say that the first feature of interest is the duration not working. Then based on this, we try to split things and say, okay, after we control for duration not working, and we know that less than 10 years outside the labor force matter with respect to more than 10 years. What is relevant? For instance, having a kids is interacting with this variable to explain our outcome. And this is going down. So this is a classical decision or regression tree. So you start, the first node is one variable, then you have binary split all around, and then you end up with predictions. It can be prediction if you're looking about regression model, classification if your outcome of interest is a dummy 0, 1. Okay, so this is one single tree. The random forest, what it does is to create multiple thousands of trees and then do a kind of averaging out all the prediction that we get to identify one single big model. So we identify one single selection of variables. The black box behind the things behind random forest is that you cannot really see then at the end how the variables are interacting, because again, this interaction that we know is the result of putting together many different trees. And each tree is trained on a subset of the data, on a subset of the variable. This is the good point, is that you're already doing extracting some variable, extracting some cases, you're putting better cases, and so doing thousands of things. And then you average out the results. And this is the random forest. And the result of random forest is a list of variables, and it's called variable importance. So for each variable, for each feature, you end up with a number that gives you the information if this variable is relevant or not. And the relevance is based on some criteria. It can be impurity, Gini, or whatever. According to the model, is slightly different, but for the sake of simplicity, we will discuss about importance in general. And you end up a list for all the features that you have in your data. You will have a number that gives you the relative importance. Higher is this number, higher is the importance of that variable to explain your. One of the issue around random forest, or one of the reasons why Boruta is an improvement with respect to the standard random forest, is that yes, you end up with this variable importance list, but then the interpretation of the value of the variable importance is very hard. It's almost impossible. Doesn't mean much. So it's then, imagine you have 100 variables, you end up with this big table of variable importance. How you decide which one you want to include and which one you want to exclude? You can say, oh, I will take the first 10. Or someone else can say, no, also the number 11 and 12 matter. Yes, the variable importance is lower, must still matter. What Boruta does, and being considered one of the best algorithms for low-dimensional spaces, and we are in low-dimensional spaces because we don't have these 100 millions of data, is to create this set of shadow features. So in addition to, like a random forest, to pick some variable and pick some data here and there, he creates an enormous set of fake variables. So imagine to have your original feature that you put in the data, the person ever moved from low to high SCS. So Boruta creates some fake shadow features or fake variables, just slightly changing the values within your variable. So you have your original variable, and then you have a series of fake variables that are very similar to the original one with just slightly modification. And what Boruta does is over the 1,000 and 100 of the tree that is running, is also comparing the fake variable to the true variable. If the fake variable and the true variable are similar in terms of ability to predict our outcome, then we'll say that that variable is not relevant. It's relevant by chance. Because some variable, fake variable that he creates out of the blue is relevant as well. So what it does is comparing all these shadow features to the true features. So one of the very good things of Boruta is that at the end, like the random forest, you end up with a list of with your list of variables, with all the list of variable importance, but there is an additional column that we will see in R, where we say that if that variable is confirmed as important or not. So it's giving you an additional information with respect to normal random forest. We say, look, these variables true have their own variable importance, but I tested and these are not relevant variables for you. So already here you can have like, you can identify a subset of variables, subset of features that really matter to explain your outcome, giving you a very specific like interpretation. Let's do this in R and then we'll see if there are questions on this. So sorry, we need to jump down in line 201. So we have, again, we have created our sequence. We have created our features that are in a variable called features. And then we want to run a random forest. Instead of running a normal random forest, we want to use this Boruta that comes in a library called Boruta. Sorry, we need to, for those who are doing it at home, we need to run also these 2 lines of code. Sorry, I realized that the slides were in opposite order with respect to our code. So we have to run first line 183 and 184, and then we go back here. We did a little bit of manipulation, and I'll explain you why we're doing this. It's because random forest, say the library of random forest behind Boruta doesn't work very well with sign in the variable name, like parentheses and stuff, because parentheses, dots, this kind of sign have a specific meaning for R. Okay, so if the variable this within the name, they can create problems. So this is a very general thing, and it happens a lot in R. In case you are running some function taken by random packages, and then it give you some error and say, oh, error names on something is likely coming from something like that, where the name of the variable should be as easier as possible. Okay, this is a very general thing. But anyway, we are running this, so let me discuss a little bit how it looks like the Boruta function. So the function is called, or we create a new outcome that's called selection.boruta. So the function is called Boruta, and then you write within the parentheses the formula, as in the usual way we run formulas in R. So we have our outcome variable, in this case y, the tilde, and on the right hand side of the tilde, all the variable inputs. Here, there is a way to include all the variables is to use a dot. Probably you cannot see here, but this is a dot here. Then you will include the name of the data sets. And then we need to give a couple of commands, a couple of options. The number of trees, so how many trees the Boruta will build, and the number of runs, how many times the iterative procedure will be done. I put here 150. This is a very low number. You usually should use 1,500, something like that. But since we'll take a little bit of time, for sake of simplicity, I have say to Boruta to run 50 trees and with the maximum run of 100. So if you're running this by yourself, you should consider increasing a lot this number. That's the best way to show the people here. So, okay. So in the console, this is the output from Boruta. So on the left hand side, the column, you have all the features that you have included in our sample, in our data set. So in this case, there are 58 of them. Then there are 4 columns that are the values of importance. This is the mean importance, this is the median importance, the minimum and maximum observed. Doesn't really matter, but you can use the mean or the median importance to evaluate the relative importance of the variable. Then you have normal hits. This is the number of times this number of times is confirmed as important. And then you have this last column. This is the relevant one, where you say that if is confirmed as relevant or have been rejected as relevant. Again, this is based on this shadow things of comparing multiple shadow features. So in this case, Boruta is telling us that the first 5 are important. So the duration, how long the person was in a condition, and also the fact of ever experience being mid, out, high, or low SCS. No, sorry, in the mid and the fact of being in a mid SCS neighborhood or being outside is considered as relevant to explain our outcome. Instead, I don't know, for instance, this. This pattern from mid to low, so someone was moving down the ladder from mid to low, has been rejected. So yes, this variable has its own importance, so it's been calculated, the relevant importance of this variable is 1.07, but it's not relevant for explaining our outcome. You can see you will have a long list of rejected and confirmed. Let's say let's look among the timing, so the one that you have at the very bottom of the slides, you will of the console, you will see that the only 2 that are confirmed as important are something that happened. So moving, so this. Moving down between age of 125, so childhood mobility downwards is considered as relevant, and actually any moving that happened between the age of 125 is considered as associated with that one. So again, Boruta, what is giving us is for each variable, for each feature, values that are so-called mean importance or median importance, and in the decision, we say, okay, this variable is really relevant, this variable is relevant. Already here, from 28, we end up to analyze probably 10 of them. So there are not 58, not all the 58 are matters to explain our health condition, but there are actually just 50, just 10 of them. Let's say how it looks like in the slides, and then we have questions. How about our empirical example on income inequality? So remember, there we had 100 features running in Boruta on a much higher number of trees and higher number of runs. We end up as important 32 of them. So already we restrict our groups of variable of interest of 1/3. And for each variable, we have this variable importance. So for instance, we say that the variable importance is very high for the fact of being alone with children. So this is only women. So income of women in midlife is strictly connected with the fact that we have been alone mothers sometimes during the life course. So the transition to partner with children is relevant. Union dissolution is relevant. So the timing of when the union dissolved is relevant, and so on and so forth. So what Boruta is telling us, for instance, in this empirical example, is that what matters to explain inequality in income later on in life is, well, this is quite expected, but the pattern of inactivity and the fact of being part-time work matter. And everything happening on the labor market after the age of 30. So at least in this group of women living in Switzerland, what matters is the working condition after the age of 30. Early on in life doesn't really is associated with the inequality in income later. The time in education, so long-term education doesn't really matter in this case, once we control all the other characteristics. About the family trajectories, what seems relevant is again single mothers. So the fact of being solo mothers or not, union dissolution is more or less the same stories. In Switzerland, is very unlikely to have kids outside of marriage. So and when instead this is extremely interesting is that many papers using this more indicators approach suggest that the time of childbearing really matter also to explain long-term income inequality. What we see in our work instead, that once you control and looking at all the interaction between things, actually the timing of childbearing, at least for this group of women living in Switzerland, doesn't really matter to explain the income later on in life. So we find a result that is slightly against the literature because we are controlling for a very large set of characteristics. So before moving to Lasso, what are the pros and the cons of this approach? The pro is that, again, I start with 118 features and end up with 32. There's still a quite large number of things to looking at, right? In our empirical example, in R, the number of features reduce a lot, but it's likely situation like this, where still Boruta will suggest you that many things are relevant. So interpretation-wise, it must be careful. We should, the way where we suggest to do things, and also the way we suggest to do things in a work that we're going is going in this direction. We should look at these features. We should look at their importance and try to identify common situation or commonalities that we are in the features to explain them in a more homogeneous and more common way, slightly to focus on one specific characteristic or the other. The pro on the other side is that Boruta, since his all relevant feature selection algorithm, can allow to give a general overview or global understanding of what happened in the data. It can allow to give us a more broad view of things that matter to explain our in our case. The next one will be based on Lasso. Before moving to Lasso stability selection, are there any questions about Boruta, but also more in general about the random forest approach to social science?
We do have a question online about the sample size, whether there is a number of trajectories as a minimum to perform this kind of analysis.
This is a very good point. When you do random forest kind of approach, since you work in this direction, you should have a critical mass. You can decide, for instance, how many individuals should be in what we call the final nodes of the tree. So the idea is how many, at minimum, how many people I want to observe here. There is no strict rule of the numbers, but you should have a minimum critical mass to identify this kind of interaction. There is also a question in the room from the.
Just asking about the slide with the tables for the importance, like the numbers 2015, it's out of 100 or is
So the value of importance, and this is true for random forests in general, or this Boruta, doesn't have a meaning per se. It's not 100, it's not out of 100, it's not out of 50, is giving you, according to the measure that you use, is how pure or impure the node is. So per se, 20 or 21 or 17 doesn't mean anything. It's not 20%, you cannot interpret in this way. The only way to interpret is to in ascending or descending order. So higher is the value, more important is this feature. So you can only say that full time not working that have an importance of 21 for 130 is slightly more important than the features of alone with children. But you cannot say it's 10% more important, less, or something like that. It just give you a general indication of the relevance. But this is a very good point. So the other approach that we try to push in a different way of looking at things are the shrinking methods. So the idea here is with Lasso, we have done a general overview of things. So again, we end up with a very long set of things that we want to analyze. And this is a way of doing the feature selection. This is the most common way of thinking. The other common way of thinking is that I don't want really to have this general overview. I really want to see which variables, which features have the stronger predictive power over my outcome. Okay? So the shrinking methods, and Lasso is one of them, is also the aim is to identify the best predictive subset of features. So the goal of Lasso is to identify that feature or that small group of features that we need. So just a brief overview what Lasso means. Lasso stands for least absolute shrinkage and selection operation. So this is I put this in a very not precise way, but just to give you an idea of how the equation looks like. So does this equation ring a bell to anybody? What happens if I do not look at the second part? This is the LS. You are minimizing the residuals, the squares residuals. Okay? So Lasso is a kind of linear regression model in which you're adding to the minimization process these coefficients, the penalization conditions. So the idea is that the data value are shrunk towards the central point, so are shrunk towards the mean. This part means that I want to minimize this penalization, and I will penalize the coefficients that are not bringing much to the estimation. So I'm penalizing, I'm penalizing towards zero, so are we excluding them then from the model, all the features that are not relevant to predict my outcome. And since we are in a kind of linear regression model, one of the negative point of this kind of approach is that interactions are not really taken into consideration. This is a big difference between random forest and the Lasso kind of things. Random forest, by the way it's constructed the forest, interaction are taken into consideration because I mean this is a first variable, this is the second variable that is identified on the base of the first one, and etc. So in a way, the interactions are already within the model. In a Lasso, that is linear. There is a kind of based on linear modeling approach. Instead, these kind of interactions are not considered there. But the good part, the things of Lasso is that can give you a very specific and detailed identification of things. So let's see how it looks like in art. So what I'm using in the paper is not Lasso directly, that you can do that, but is another library that is called stubs or stability selection. The stability selection is a kind of a step forward with respect to the normal way of doing Lasso, GLMNF, etc. So they're adding a little bit more complexity to things, and they're an additional kind of bootstrapping or resampling things to be sure that the features that you select are the stable one. This is the name stability. So the fact that you identify that feature is relevant is really because it's relevant and not because by the chance of the model. So it's just adding a little bit more computationally to the normal Lasso approach. So the function we will use is called stub cell or stability selection, where again, the way of writing the equation is very easy. You need to give them an x. So the x variable for our set of features, so a set of x variables. You need to give them the y variable, so which is the outcome of interest. So in this case, I'm saying that the y variable is the variable outcome in our dataset data frame 2. Our x variable are all the features that we are interested in. And then you need to give them what is called the fit function. So you say which function you want to run, because this subit selection is a very general approach. You can use different kind of algorithm within subit selection. In this case, I'm saying I want to apply the subit selection algorithm or this recursive approach on a Lasso kind of estimation. And you have, in this case, 2 parameters to include, the so-called per family error rate or PFER and the cutoff. So, and the number of subsampling replicate. So again, the idea of subit selection, in addition to the Lasso and etc., is doing iteratively over multiple subsampling. So you need to give them the number of subsampling you want to, the subsample that you want to run things, and these 2 coefficients, parameters. So I don't have the time to keep going in the detail also because it very much depends if you want to use Lasso or other kind of approach, but I'm using here a PFR of 1 and cutoff of 0.6 that are the ones that are suggested by the authors. If you go back, if you're interested, the stability selection paper is very well written with a lot of tests, and then you can really understand what these values means and how to set the parameters of the function. So let's see how things look like. So what stability selection does, or what actually Lasso does, again, is giving you a penalization for the different features. You decide the cutoff. Again, the cutoff that I chose was at 0.6. The authors says that any value between 0.5 and 0.7 are good for prediction purposes. Again, this is mathematical reasons that you can, if you're interested, you can go back to the paper and look at, but I'm using 0.6 as suggested by the authors. So the cutoff is at 0.6. So what they're giving you for each feature, if you are above or below this cutoff, or this pi square, the selection probability. So if you are passing or not the cutoff given, then you decided the PFL output. So in this case, so I'm saying that I'm selecting the variable that pass the cutoff at least 60% of the time. In this case, the variable, if you're looking at the outcome, it will say which are the variables that are selected. In this case, are selected the duration of low, so how long the person has been in low SES neighborhood to explain our outcome of interest. The fact that the person was moving between the age of 1 and 25, and any moving between the age of 1 and 25. So according to Lasso, these are the three situations that really has the highest predictive power over our outcome of interest, our health. So in our example, it seems that the health condition later on in life depends on how long the person has been in a low SES neighborhood, the fact that the person has moved from a high to low SES between the age 1 and 25, and or if the person have had any movement between the age 1. All the values that you can see here, so the selection probabilities, can also be represented graphically. We simply use a plot, like, and the name that I've given to this object. And you can see really clearly from the plot that these three variables are really the one that made the cut of 0.6. All the rest are really skewed to the left, so towards 0. Perhaps these are ordered according to the number of times that we passed the cutoff. So the first is the 125 moving, etc. Then perhaps, so we have these three dots are the first three variables. Then thanks to the plot, we can also see that, for instance, the duration out, so how long the person was living outside Santiago, is somehow related to this health outcome that we have, but not enough to make the cut. But again, this is a good example of how to represent, for instance, the results from a Lasso study selection process, showing how many times the features are able to make that data. So again, what are the key message here that we got from Lasso is that what matter is the duration low, so duration in low SES, and the fact of moving in a very early in life. Boruta, as you might remember, that looks very nice. So remember that we have run our stability, our Boruta algorithm, and we end up with this table that I've discussed before with the mean importance, etc. To make things a little bit easier to understand, we can also say, okay, let's focus now only on the features that are confirmed as important. So the one that Boruta says, oh, this is the relevant one. A bit of error coding. So given this is our object, are this table here, I want to subset only the variable, the lines where the decision is confirmed. So now I can end up with something that is much more easier to look at. So these are the list of features that, according to Boruta, are considered as relevant, and these are the relative importance. So according also to Boruta, what is most, and then we can doing like a graphical representation of this value. Now it doesn't look very nice on the screen right now here on the bottom panel of the plots, but you can play a little bit better with the ggplot and to make this look nicer. But what we say to the Boruta again is that duration law for how many years matter is relevant. Also, according to Boruta, the duration of in a mid-SES country enabled matters for clinical health. And again, this moving at a very early age. Plus, also some pattern here and there. So actually, what you see is that the results of Lasso and the results of Boruta are not that different. So Lasso is giving you a kind of subset of what Boruta has considered as important. And this is made the case in any of this kind of application, because again, Boruta the goal is to have a more general overview of things. Lasso is going straight to the point, to the predictive power. So it's common that all the features that are considered as relevant in approach and random forest are also the ones that are considered as relevant in Lasso. So that's the reason why it's good to interpret both at the same time. So are there any, I know that this is a lot, but are there any questions?
Not online.
Not even here. So let's go towards the conclusion of this. That we are already quite a long session.
We do have a question.
Okay.
So just arrived. So the question is, these two methods allow us to understand somehow the score of importance of the variables, but how to understand whether they are negatively or positively correlated with the dependent variable.
So this is a very good point. So either Lasso, you can run, for instance, let's focus on Lasso first and then run Lasso, not stability selection, but Lasso in general. You can also ask Lasso to run a sort of linear regression later, only on the variables selected as relevant, and then you will have information about positive or negatively associated with you. But this is not the goal of the selection process. The goal is to identify which one are more or less associated. With random forest, again, you have also only this variable list of importance, and what you can do is to create what they call partial dependence plots. The partial dependence plots are something that happen later with respect to the estimation of the random forest, and is calculating a sort of average marginal effects. So it's very similar to the idea of average marginal effects. For instance, this is again took from the example on the women income, and the yellow is the average marginal effect estimated. All the black lines are the estimates that we have for every single case. So it can also give you an idea of distribution of the confidence interval in a way. As you can see, we can see there is a positive effect on income of moving from not having ever experienced being alone with children and having the children. It is a positive effect of 0.12 in terms of average marginal effects. In the sense that women that had kids had to work more. So at the end of their life, they will have a higher wealth. The wealth is due to the fact that they had to work more hours because they, in a certain moment of life, they've been alone with children. And this is very common in many cases. It is similarly common in the Swiss case that are, again, the sample behind the study, because women in Switzerland tend to work less than full time. And then when they need, they go back to the labor market and increase their participation. What we're looking on the right is the same things, but with a continuous variable. This is duration of working, where you can see there is almost a linear negative effect on wealth until a certain point. So it means that having one additional year of not working is negatively associated over a given amount. I don't have now the number in mind, but up to a certain point, like after 5 or 6 years, after a spell of 6, 7 years, then it becomes quite stable. That means that these are women likely that are already outside the labor force, but for some reason, perhaps they have other income, perhaps it's the income of the partner or the family, whatever. This is only women income. So the reason I'm showing you this is that that's the way of looking at non-linear relationships. So one good thing of Boruta, unlike like a normal linear regression model, where if you add a continuous outcome, a continuous variable, the idea behind is to have a linear association between that outcome and the variable of interest. Boruta automatically check for nonlinear relationships. So using this partial dependency plot, and then you can do this for any of the features that you have in the data. You can do this interacting the features. So you can also say, how looks like the average marginal effect of duration not working once I interact with having or not experienced a lone motherhood. And then you can bring this and to interpret this. How to do that? I do not include it then at the end of, I think, of this R code, but here, for instance, you have in line 256 or something like that, a library called IML is one of the libraries that allow you to create this kind of plot. There are many libraries in R where you can create this partial dependency plot. So the step is you create a random forest first, and then based on the random forest, you calculate this prediction, these marginal effects, and then you plot using this partial dependency plot. So this is the way after a random forest to interpret the direction of the results. Since there is a little bit of coding, I did not include this in here, also because there are many different libraries where you can do that. Some are more easy to use, some are give you more information that you can use and set. But thanks for this question. This is very relevant, and I wasn't sure to at the time. So let's go back to So going back to our results, we found that duration law is important, moving down is important for Boruta, but these are also the same features that were relevant for stability selection, right? So we found very similar results. And this is, again, true in many cases, but I also have a confession to make. In our dataset, there were no health indicators. So I created health indicators, simulating the results based on some features. So I ran a fake regression model. I simulated the value of these potential health indicators based on exactly that feature, the duration of law and the fact of moving. Okay. Then, of course, during doing Boruta and Lasso, you will find the same results. Okay. But even if, because in case you end up using that data set of residential mobility, you will not find this outcome variable, because I create this outcome variable out of blue just for the sake of this presentation. But anyway, this is a very common result. I tested it over multiple data sets, over multiple outcomes, continuous, discrete, with discrete outcome, with discrete features, continuous features, whatever. And the results are always more or less similar. And this is also similar by construction of the algorithm. Boruta Lasso tends to have a small subset of the features that are also considered as relevant with Boruta. Okay? This is not completely out of it. So, just to conclude, and going back to square one, where this came from is, okay, people are using sequence analysis to analyze these cumulative advantage and disadvantage theories. So I have the sequence, I create a cluster, and then I see if the clusters are associated or not to indicate to an outcome variable. Where the problem here is oversimplification. It's very difficult to identify the key aspect of these groups that really matter, and also statistically are less efficient results. The other approach is the indicator one. I create a priori 2-3 indicators or variables that are explaining some theoretical hypothesis, and then I use this in the model in the regression step. Okay, but you need to justify why you chose that specific feature against that specific feature in matrix point. What we try to do in this feature selection approach is try to look at both things at the same time and say, let's identify all the characteristics of the life trajectory, so all the characteristics, all potential relevant characteristics, and let's identify these features using feature selection algorithm. Let's triangulate the results between Boruta and Lasso or other feature selection algorithm. But again, what we are proposing is not alternative to other approaches, it's just to overcome some of the issues that we have seen in applied research. It is an improvement with respect to classical model-based regression approach, because for instance, with Boruta you have all this interaction, you can account for many different things that you cannot do directly in a regression model. And it's somewhere between an exploratory and an explanatory tool, in a way. Is it exploratory because you extract many features and you identify what is relevant for your outcome. So it's an exploratory tool, but can also be seen, that, for instance, using the partial dependency flow that we have seen a few minutes ago, can also see in a way, an explanatory way, in the sense, okay, this matter because the direction is positive or negative. What we believe is that this contributes what they call a discovery phase in many social science perspectives. So a thick description of the reality, a thick description of the data. And this also can be considered as a way, as a starting point. You can have your new data that with new longitudinal data that you perhaps don't know very well. And then you can apply this kind of method to have an idea what's going on in the data. And then you can go back to the square one and you can create your hypothesis and start with other type of approach, knowing how the data look like, how the data are performing, how the associations are. This is a final point that I will not want to discuss, or better, I want to just give you like a general questions. We in social science, in sociology, social demography, we think there's a lot of discussion about data science in society. These machine learning techniques, can we use the machine learning? So something that are algorithm based, where there is very few intervention from us to create hypotheses. So are this machine learning also a way a priori to run the data and say, okay, I observe this, I can create an hypothesis, or can I create new theories based on the analysis of multiple data sets and see what's going on thanks to the machine learning, instead of testing one specific things at a time. I think I will conclude here. Are there any final questions? No, otherwise, I think I will thanks everybody also that are following this online. I know there's a lot of material, I know there's a lot of stuff that I've packed in 1 hour and a half for 2 hours class. Thanks everybody. Thanks to IUSSP for the support. And anyway, if you have any other questions, here you find my email address, or don't be afraid to write to me and ask, and we can discuss about things in more detail. Thank you so much.